Hello, my name is Austin Abbott. I'm a graduate student at the Texas A&M Cyclotron Institute, and today I'm going to talk to you about my work involved in characterizing and correcting effects on measured excitation energies in DAPR. DAPR is the detector array for photons, protons, and exotic residues, which we constructed at Texas A&M for the purpose of measuring photon strength functions of excited nuclei produced in DP gamma reactions. And it is placed at the end of MARS, which is the momentum achromat recoil spectrometer. So photon strength functions are important. They describe the gamma ray emission probability of excited nuclei, and this is essential in understanding the production of elements and isotopes in neutron capture reactions like in nucleosynthesis. Our reaction was the iron 57 DP gamma iron 58 reaction in inverse kinematics, and we will use this to extract the photon strength function of iron 58. I will go through each section of this poster in separate slides. So to start off, we have the experiment. It was between August 2nd and the 17th. This is a CAD drawing of DAPR. The beam comes in from the right. In our case, it was iron 57 at 7.5 MeV per nucleon. In this T here, we have our annular silicon detector and a deuterated polyethylene target. The beam passes through a hole in the center of the silicon. The reaction occurs in the CD2 target, and then the protons emitted between angles of 120 and 155 degrees get detected in the silicon detector. We use the measured proton energies to then calculate the excitation energy of the iron 58 nucleus. The green cylinders here represent the barium fluoride detectors. We have 128 of them. They're used to detect the photons that are emitted from that excited nucleus. Here's some pictures from the experiment. If we look at some preliminary data here on the right, on the top I have the E gamma EX matrix for the uncorrected spectrum. This is the raw data. See, there's nothing super interesting here, but when we apply carbon subtraction using a carbon target run, we see some lines that represent particular populated excited states and the gamma rays emitted from those states. So this is promising. If we look deeper into the data, I plot the excitation energy spectrum for the iron 58 nucleus with a particular gamma ray energy gate on it to improve my signal to noise ratio. I can see that for the second excited state in iron 58, 1.675 MeV. However, when I fit this and pull the mean value, I find that over the course of the experiment, the peak position shifts around quite a bit. We also found that during the course of running on a particular CD2 target, we were actually depleting our deuterium content. And so we would actually move our target periodically throughout the runs in order to hit a new spot in order to increase our deuterium percentage. And so this plot here represents the loss in the deuterium over the course of running on a particular beam spot. However, we noticed in one particular case here, we were using one beam spot, so we hadn't moved it yet, and we see that there are shifts in the percent deuterium. So this could be indicative of the beam actually moving around. So this causes problems in calculating the excitation energy because we are assigning the wrong angles to our protons and we're getting incorrect proton energies. We calculate this percent deuterium by using the ratio of a carbon subtracted excitation energy to just the CD2 excitation energy spectrum. And so in this case, it would be the ratio between this black spectrum and this blue spectrum here. So the beam actually burns away part of our deuterium, and so this reduces the thickness of our target. In this way, our energy loss correction is actually changing, and so this can have a large effect on our low proton energy, which would be high excitation energy. This is the high excitation energy peaks are not easily resolvable in the iron 58. However, we did a calibration beam of carbon 13 where high excitation energy states are clearly visible. However, you can see that they are shifted, and so this could explain the shift here at these low proton energies. The beam spot actually moving on the face of the target over the course of a particular run could explain the shifting of the excitation energy peaks for this lower excitation energy, which would be a higher proton energy. And so how are we going to correct for these problems? So in the lab, we're correcting for the target thickness by putting the targets that we used in the experiment in between a thorium-228 alpha source and a dual-axis dual-lateral silicon detector, or a DATL. This is position-sensitive detector. So the alpha particles from the source pass through the target, losing some amount of energy based on the thickness, and then we get the remaining energy in the DATL. And using this information, I can generate a thickness map of the target. And so we'll be able to use that to correct for energy loss. And then our beam spot correction, we are running through different beam spots on the target to see which minimizes our width. And so if I assume a 0, 0 position for the beam spot, I get a sigma of 0.496, and a mean of 1.97. However, when I apply a new beam spot of 1.1, 1.1, I find that my sigma is decreased to 0.353 and my mean to 1.83. And this is because we're now assigning the proper angles to our protons. And so with that, I'd like to thank you for your time.